Slide 1. The Atmosphere and Winds, Topic 08A, Part 2, Clouds and Rain. Slide 2. As air rises, it cools due to the reduction in atmospheric pressure. Air mainly consists of oxygen molecules and nitrogen molecules. Remember that warm molecules move faster than cold molecules. This allows warm air molecules to push aside nearby molecules and spread out, which lowers their density and causes them to rise. Atmospheric pressure is caused by the weight of the air above. Up in the mountains, air pressure is lower, because there is less atmosphere above you, less air pressing down on top of you. Therefore, as warm air rises higher into the atmosphere, it experiences lower pressure. Since the group of warm, rising air molecules are no longer being squeezed together as strongly by the air above, the group of warm, rising air molecules pushes outward. In other words, the warm air expands as it rises. However, in pushing outward against the neighboring cooler air molecules, the warm, rising air molecules give some of their energy to the neighboring air, causing the warm, rising air to cool down. In short, rising air cools due to the decrease in atmospheric pressure. Experiment: blow into your hand. First, keep your mouth opening small, then open wide as if yawning. In which case does the air feel warm? In which case does it feel cool? When the opening is small, the air is forced together, and quickly expands once outside your mouth. If the water molecules in the air cool down enough, they will begin to bond with one another. The water molecules are no longer moving fast enough to fly apart when they get too close to one another and bonds form between them. Thus, rising air produces cloudy and rainy skies. As the rising air cools down more and more, it loses its water as rain. By the time the air sinks, it is completely dry. Dry air cannot produce clouds or rain. Note: in most situations water vapor needs additional help from aerosols to condense. Aerosols are tiny solid particles like dust or drops of liquid in the air. It is easier for water molecules to bond with bigger, slower moving objects like aerosols. The kind and size of aerosols available can have a big impact on whether clouds form and rain occurs, as well as how much rain occurs. Slide 3. Convection cells, and cloudy skies and clear skies. In the previous unit, we learned that as air rises, it cools, causing the water vapor in the air to condense into clouds and rain, if enough water vapor is present in the air. If we apply this idea to a convection cell, clouds and rain will be more common above the warm spot, the place where air is rising. The sinking air at the cold spot will have little or no water vapor, because the water vapor was lost at the warm spot when it condensed into clouds and rain. In addition, the air at the cold spot warms as it sinks, due to the increase in pressure. So, clear skies will be more common above the cold spot. Slide 4. Air temperature, pressure, cloudy skies, and clear skies. If you listen to weather reports, you may be familiar with the fact that low pressure zones are associated with clouds and rain, and high pressure zones are associated with clear skies. Beneath regions of warm, low density, rising air, the pressure at the surface of the Earth is lower. There are fewer air molecules above. Beneath regions of cold, high density, sinking air, the pressure at the surface of the Earth is higher. There are more air molecules above. Here is another way to think about this: if the air is rising, going up, then the air is not pressing down very hard, and if the air is sinking, going down, then the air is pressing down harder. We have learned that warm, rising air produces cloudy and rainy skies, and that warm air exerts lower pressure, so lower air pressure at the surface is associated with cloudy and rainy skies. Cool, sinking air produces clear skies, and cool air exerts higher pressure, so higher pressure is associated with clear skies. Also, note that we learned in the previous unit that air moves from the colder spot to the warmer spot to replace the air rising at the warm spot. In other words, winds blow away from the colder spot and towards the warmer spot. Since the air at the colder spot exerts higher pressure and the air at the warmer spot exerts lower pressure, this means that surface winds blow from the place with higher pressure at the surface towards the place with lower pressure at the surface. Slide 5. The global rainfall pattern. You need to be familiar with the global rainfall pattern shown on the slide, as well as the global wind pattern. If you know where surface winds come together and the air rises, then you know where it is cloudy and rainy. Similarly, where surface winds move apart, air sinks, and the skies are clearer. Remember that the dotted arrows show air rising and sinking, air going towards or away from the surface of the Earth. Air rises at the equator since it is the warmest place in the world. As the air rises, it cools, and this causes water in the air to condense into clouds and rain. Hence, the equator is where we find tropical rainforests. At the cold poles, air sinks and thus there are clear skies. Air moving away from the poles and equator turns under the influence of the Coriolis effect, so it cannot travel all the way from the equator to the poles or from the poles to the equator. As a result, air sinks at 30 degrees north and 30 degrees south where it is cooler than the equator, and air rises at 60 degrees north and 60 degrees south where it is warmer than the poles. The rising air at 60 degrees north and 60 degrees south leads to cloudy and rainy skies at these latitudes, and the sinking air at 30 degrees north and 30 degrees south leads to clear skies at these latitudes. To help remember this, think of Southern California and Seattle. Los Angeles is close to 30 degrees south, so we typically have clear skies. Seattle is the closest big city to 60 degrees north along the west coast of the United States, and is known for its gray skies and rain. Slide 6. Weather, climate, and fronts. Up till now, we have been discussing climate, not weather. Climate is the long-term average of weather conditions, what the weather is usually like. For example, Southern California has a warm, dry climate with clear skies. This does not mean that it is always warm or that it does not rain in Southern California. It means that our weather is warm most of the time and that rain is less common here than elsewhere. Here is another way to think about it: weather is what conditions are like on a particular day, while climate is what conditions are like during a season or a year. Your own experience of actual storms and rain may contradict something that I said before. I claimed that warm, rising air leads to clouds and rain. Many of you may say, wait a minute. It rains when the weather is cold. Storms often form along what meteorologists call fronts, a place where two air masses meet. An air mass is a collection of air with similar properties, like temperature and water vapor content, often determined by where it comes from. For example, warm, moist air moves up into the United States from the Gulf of Mexico, while cool, dry air comes down from Canada. We also use the word front to describe the location where two opposing armies meet and are shooting at one another. As in the military, the front lines for weather typically are where the action is: clouds, rain, hail, snow, and so on. At the locations where air masses meet, the front, the cooler air pushes the warmer air up, sliding in underneath to replace it, or the warmer air can move up and over the cooler air. As the warmer air rises, it becomes cooler, and if the change in temperature is strong enough and the rising air contains enough moisture, the water vapor in the rising air will condense into rain. If the warmer, rising air does not contain water, there cannot be rain along the front. Thus, the weather is cooler when it rains, because cooler air is coming in and lifting up the warmer air. Remember, the warmer air might not be very warm. It is just warmer than the cooler air on the other side of the front. Slide 7. Distribution of heat from the sun. In this section, you will learn why temperature changes with the seasons, why some parts of the world are warmer than others, and how the motion of the ocean and atmosphere keep the warm places from getting too hot and the cool places from getting too cold. The equator is warmer than the poles, because it receives more heat from the sun. Sunlight shines directly down upon the equator, but approaches the poles at an angle. As a result, sunlight is spread out over a wider area at the poles. In other words, sunlight is less concentrated, so these places are colder. The second most important factor is that much of the poles are covered by white snow and ice. As we learned in Unit 2A-1, white substances reflect all colors of light well, so the white snow and ice help reflect sunlight back into space and prevent it from helping to warm up the poles. In addition, sunlight that comes in at an angle is more likely to get reflected back into space rather than absorbed, irrespective of its color. Moreover, sunlight coming in at an angle passes through more of the atmosphere, so the atmosphere absorbs a little bit more light than normal. Here is an experiment that you might try. Get a flashlight. Hold your hand flat with your fingers pointing towards the ceiling. Hold the flashlight horizontal and shine it on your hand. Now, tilt your palm upwards towards the ceiling. What happens to the circle of light on your hand? You can see how sunlight is spread out at the poles because it strikes the surface at an angle. Slide 8. Heat distribution and the seasons. The angle at which sunlight approaches the surface of the Earth also helps to explain why some parts of the year are warmer than other parts of the year. In other words, it helps explain why there are seasons. Notice how the Earth is tilted relative to the Sun in the diagram on the slide. In other words, the North Pole is not pointing upwards on the page, and the South Pole is not pointing downwards on the page. The Earth's North Pole always points towards a star we call Polaris, also known as the North Star. As the Earth orbits the Sun, its tilt never changes. In other words, as the Earth goes around the Sun, the North Pole remains pointing in the direction of the North Star. The Earth's tilt is called its declination. During our summer, the Northern Hemisphere is tilted towards the Sun, so we get more sunlight in the Northern Hemisphere and become warmer. In other words, the warmest spot on the Earth is north of the equator. On the other hand, the Southern Hemisphere is tilted away from the Sun, so it gets less sunlight and becomes cooler. Thus, it is winter in the Southern Hemisphere when it is summer in the Northern Hemisphere. It takes the Earth 1 year to travel all the way around the Sun. So, 6 months after summer in the Northern Hemisphere, the Earth will be on the other side of the Sun. The Earth's tilt does not change, the North Pole always points towards the North Star, Polaris, so now the Northern Hemisphere is tilted away from the Sun. In other words, the warmest spot on the Earth is south of the equator. We get less sunlight during this part of the year, so it is our winter. However, more sunlight is falling in the Southern Hemisphere, so it is their winter. Thus, Northern and Southern Hemispheres experience opposite seasons. When it is summer in the Northern Hemisphere, it is winter in the Southern Hemisphere. When it is fall in the Northern Hemisphere, it is spring in the Southern Hemisphere. And so on. These changes occur due to the orbit of the Earth around the Sun over the course of the year. Sometimes more sunlight falls north of the equator, sometimes less, causing the seasons to change. The change in the amount of sunlight occurs because the North Pole is always pointed towards the North Star, Polaris. During some parts of the orbit, this orientation exposes more of the Northern Hemisphere to the Sun. When the Northern Hemisphere receives more sunlight, the Southern Hemisphere receives less sunlight. During other parts of the orbit, less of the Northern Hemisphere is exposed to the Sun. When the Northern Hemisphere receives less sunlight, the Southern Hemisphere receives more sunlight. Note, the Earth's tilt wobbles a little bit very slowly in a small circle over thousands of years due to the gravitational pulls of Jupiter and other planets on the Earth. So it has not always pointed towards the North Star, Polaris. Slide 9. Temperature distribution and heat emission. The temperature of a place is not merely a matter of how much heat it receives, because if an object only gains heat, then it continues to get hotter and hotter. Objects also lose heat by sending heat into the neighboring environment. Heat is conducted away by direct contact, as when your hand touches a cold surface, heat flows from your hand into the cold surface. Heat is also radiated away as infrared light. Infrared light is invisible to us because our eyes cannot capture it, but we can feel its heat when we get close to a hot object, like an electric stove burner when it is on a low setting. Irrespective of how the heat is lost, the basic rule of heat loss is, the hotter an object is, the the more heat it sends away. As an object gives away heat, it cools down, and therefore it gives away less and less heat over time. Even frozen objects give off heat, and therefore get even colder. They just get colder slower and slower over time. Every moment of the day and night, the Earth gives away heat to the atmosphere, via conduction, and radiates the rest towards outer space as infrared light. Over 99% of the atmosphere is made of nitrogen and oxygen. Infrared light goes right through these gases. The remaining less than 1% of the atmosphere includes greenhouse gases like carbon dioxide and water vapor, which absorb infrared light, capturing its heat and keeping the heat in the atmosphere. The heat in the atmosphere is eventually radiated into space too, helped by the fact that warm air rises upward due to its low density and thus helps transport the heat through and above most of the greenhouse gases. The Earth does not run out of heat, because it gains more heat each day by absorbing visible light from the sun. Note, right now the Earth is retaining more heat than in the past, because levels of greenhouse gases like carbon dioxide have been rising rapidly, primarily due to burning fossil fuels like oil and coal to power vehicles and generate electricity. The poles are colder than the equator, so they give off less heat than the equator, but they still radiate heat into space as infrared light. Interestingly, observations from satellites show that the poles give off more heat as infrared light each day than they receive from the sun. Similarly, the equator radiates less heat into space than it receives from the sun. If the poles are sending away more heat than they receive, they should get colder, and if the equator sends away less heat than it receives, it should get warmer. But, of course, they are not getting warmer or colder. Their temperatures are stable, aside from global warming. An object's temperature is stable, does not increase or decrease, if the amount of heat it receives is exactly equal to the amount it gives away, just like how your bank account won't go up or down if the deposits are exactly equal to the withdrawals. Slide 10. Temperature distribution and the motions of the atmosphere and ocean. The temperatures of the poles and equator are not increasing or decreasing, because the ocean and atmosphere are moving and transporting heat from the equator towards the poles. In convection cells, the cool air moves away from the cold spot and towards the warm spot. The air from the cold spot absorbs heat from the warm spot, cooling the warm spot. Similarly, the cold spot cools the air above it. In other words, heat goes from the air to cold spot, warming the cold spot. Thus, the air moving in the convection cell is cooling down the warm spot, the equator, and warming up the cool spot, the poles. As we will see in the next lecture, the ocean does the same thing by moving warm water from the equator towards the poles and cool water from the poles towards the equator. The movement of water between the ocean and atmosphere also plays an important role in transporting heat from lower latitudes, near the equator, towards higher latitudes, near the poles. Warm ocean water evaporates under the clear skies near 30 degrees north and 30 degrees south, moving heat from the ocean into the atmosphere. Remember, the hot, fastest moving water molecules tend to be the ones that evaporate. Some of the air moves towards the poles in the winds called the westerlies, the convection cells between 30 degrees north and 60 degrees north and between 30 degrees south and 60 degrees south. As the air moves north, the air gives up its heat to the cooler ground beneath, causing the water vapor to condense into clouds and rain and return to the ocean. Thus, the motion of the atmosphere keeps the poles from becoming too cold and the equator from becoming too hot. As the air moves, it carries the heat away from the hot places and moves cold air away from the cold places. The motion of the ocean currents, performs a similar job, making the Earth a much more pleasant place to live, especially if you live closer to the equator or closer to the poles.